continue. Question 4b. So this question asks us to diagonalize A and use it to show this. We just try to diagonalize first and see what can we do after we diagonalize A. Okay, so we just try to diagonalize A first. So from part A, we know that our A is this. So to diagonalize this, I need to find the eigenvectors of this and the eigenvalues first, then find the eigenvectors corresponds to the eigenvalues and see whether blah blah blah. Okay, so okay, I'm sure you know already, we have done this quite many times. So we consider 0 equals to the determinant of lambda I minus A, and this is the determinant of lambda minus 1, 1, minus 1, minus 1, and lambda. And this is lambda minus 1 times lambda minus 1 times minus 1 is 1. So this is lambda square minus lambda minus 1. I don't think the root will be nice. So let's just do this. Minus b plus minus square root b square minus 4ac divided by 2. So I have 1 plus minus square root 5 divided by 2. And this number appear here. Okay, so it should be correct. We should be on the right track. Then we try to find the eigen factors. Okay, for lambda equals to 1, say the one with plus first, okay, we find x that is not 0, such that just write lambda I minus A, it's normal bracket, x is equal to 0. In other words, what is lambda I minus A? With this lambda, I will have minus half plus square root 5 over 2. Here is minus 1. Minus 1, here is half plus square root 5 over 2 times x1, x2 is equal to 0, 0. Okay, and try to expand this. I will have minus half plus square root 5 over 2 x1 minus x2. Here is minus x1 plus half plus square root 5 over 2 x2. Okay, let's make use of this trick. This lambda will make the determinant of this to be equal to 0, and this is homogeneous linear system, so there will be infinitely many solutions. Okay, there shouldn't be a unique solution. Okay, it shouldn't be a unique solution. It must have infinitely many solutions. What does it mean? It means that there should be free variables here. three parameters here. Okay, it also means that one of the equation should be useless. What I mean by useless is if you can find a solution for this, for x1 and x2, it must be consistent with this. Okay, let's just try it out instead of simplifying this. Okay, so let's say I want to make my x1 to be free, the free parameter. Then my x2, okay, if I use the first equation, my x2 must be minus half plus square root 5 over 2 times t, where t is real number. Okay, just want to check whether this is correct or not. I substitute this, okay, substitute this into the second equation. So I will have minus t plus half plus square root 5 over 2 multiply with minus half plus square root 5 over 2 t. This is a plus b, a minus b, so a square minus b square. And this is plus 1, so minus t plus t. Sorry, this is, okay, sorry. So this is minus, this is plus, right? A plus b, a minus b. So, and this is plus 1, right? So minus t plus t is equal to 0 for any t. So this also this is also a solution for the second equation. Okay, so we are done. We have found this as my x1 and x2. Erase this. So hence my x is just, I can take out my t, 1 minus half plus square root 5 over 2. T is real, and we can take this as my eigenvector. Okay, good. But this may not be good because I don't know, I just cannot find this number here anymore, right? So because I think this should be useful later. Okay, we might use this number later, and it is not here. Okay, so I try to change this. Okay, I try to change this. I don't know whether this will work or not, but I just try to change this. Let's try to use the second equation instead. So if I use the second equation, and if I let my x1 to be t, sorry, my x2 to be t, then my x1 is just half plus square root 5 over 2 times t. you can check yourself. If you sub this into the first equation, it should work also. So now you see this number, it appears here. Okay, maybe this is better, I don't know. Let's just try. So I have half plus square root 5 over 2. This is 1. Okay, good. Next, I need to find the eigenvector for the other one. Okay, let me do it here. So for lambda equals to 1 minus square root 5 over 2, we need to find x that is not 0, such that lambda I minus a times x is equal to 0. 0 vector. Okay, in other words, it's my lambda I minus a. It is this. Okay, it is this. So I will have minus half minus square root 5 over 2 minus 1 minus 1 and 1 over 2 minus square root 5 over 2 multiply with x1 x2 is equal to 0 0. Same thing. This gives me minus half minus square root 5 over 2 x1 minus x2 minus x1 plus half minus square root 5 over 2 x2 equal to 0 equal to 0. Okay, we make use of the same trick. We ignore one of these, and I will use the second one. I will use the second one because this number appears here. It's just because this number appears here. Okay. So we will have, if I make my x1 to be t, or okay, if I make x2 to be t, I will have my x1 is equal to half minus square root 5 over 2 t. Hence, my x is t times half minus square root 5 over 2 and 1. My t is just a real number, and we can use this as our eigenvector. Good. So, since the set containing this vector and this vector is linearly independent, okay, since the set of half minus square root 5, let's use plus, over 2 comma 1 and half minus square root 5 over 2 comma 1 is linearly independent, this matrix A is diagonalizable. Okay, A is diagonalizable. with P is equal to half plus square root 5 over 2, 1, half minus square root 5 over 2, 1. With P to be this, and okay, actually this number looks very familiar. This number looks very familiar. It is actually our lambda. Okay, so let's call, and we see that this is an observation to make our life easier. We don't need to keep writing this. Okay, I just realized this, okay, is the same as this. Okay. And this is the same as this, right? So this is basically, if I call this as lambda 1, if I call this as lambda 1, and this, I call this as lambda 2, so I can rewrite this as, okay, let's just write it from the start. So this is lambda 1, this is lambda 2, this is lambda 1, this is lambda 2. So this is just, okay, to make our life easier, I write this in terms of lambda 1, lambda 2, 1, 1. Okay, good. So and D, okay, which is the matrix lambda 1, 0, 0, lambda 2, okay, is just the multiplication of what? Let's see this. This is clearer. Okay, never mind. It is P inverse, okay, AP, right? Okay. Okay, good. Let's call this D. Okay, we are done with the diagonalized part. Use it to show that Fk is equal to that. So how? How to do this? So now we know that A is diagonalizable, okay, with this P as the matrix, and my D is this. Now I want to find Fk. Okay, let's think a bit. Where is my Fk? My Fk, okay, UK plus 1 is actually Fk plus, can't remember. Fk plus 1, Fk, right? And I can express this in terms of A times Fk Fk minus 1, right? Alright, good. So my Fk appears here. Okay, my Fk appears here. And if I just multiply by a. We don't know what is this, right? We don't know what is this. So this is difficult, but we can change this, okay, into another form, which is a times fk minus 1, fk minus 2, and this will be a squared, right? This is just a squared. And we still don't know what is this, right? But we can always continue this. We can always continue this until the number that we know. What is the number that we know? It is f0 and f1, right? If we can reach this, then we know what is f0 and f1, because f0, okay, f0 is just 0, right? f0 is just 0. And this is just 1. So I can write this as 0 and 1. And what will happen here? What will happen here will be from fk to k minus 1, I need to move one step. So I need to, from here to here, I multiply by a. From here to here, I multiply by a squared. So from 0 to k, I'm actually moving k steps. So this is actually a to the power of k, right? And since a is diagonalizable, we can write this a to the power of k in terms of p d to the power of k, p inverse. Okay, and multiply this with 1, 0, and I hope that I will get this fk term because of this. Okay, this is the thought process. Hope it works. So note that uk plus 1 is equal to a times uk, and okay, I should use uk is a times uk minus 1 okay, and we can write this in terms until a to the power of k u0, right? So from here, we can write this a to the power of k. Since a is diagonalizable, we can use the result from question 2. We have p d to the power of k, p inverse u0, right? So, and this u0 is 1, 0. Okay. So what I need to do is just find this. Okay, find this. So we have d to the power of k is just lambda 1 power of k, 0, 0, lambda 2 power of k, and P inverse is what? 1 over lambda 1 minus lambda 2 multiply with 1 lambda 1 minus lambda 2 minus 1. So, okay, and I think this is quite nice. This should be this minus this, okay, and it will be square root 5. Try to see whether there is square root 5. Okay, good. There is 1 over square root 5 here. Okay, so we should be on the right track. So this is equal to 1 over square root 5 of 1 minus lambda 2 minus 1 lambda 1. Hence, we have P d double of k P inverse is just lambda 1 lambda 2 1 1 multiply with lambda 1 power of k 0 0 lambda 2 power of k times 1 over square root 5 multiply with this 1 minus 1 minus lambda 2 lambda 1 times 1 over square root 5. So this 1 over square root 5 multiply with this times this, I will get lambda 1 power k plus 1. This multiply with this, I will get lambda 2 power of k plus 1. This is lambda 1 power of k, and this is lambda 2 power of k. Okay, I need to multiply with 1 minus 1 minus 2 lambda 2 lambda 1. And this is equal to this, I multiply with this, I will get lambda 1 power of k plus 1 minus lambda 2 power of k plus 1, and this multiply with this, I will get lambda 1 power of k plus 1 lambda 2 minus sign plus lambda 1 times lambda 2 power k plus 1. Okay, for this I will have lambda 1 power 1 power of k minus lambda 2 power of k, and this side I will have lambda 1 power of k minus sine lambda 2 plus lambda 1 times lambda 2 power of k. Okay, it is very long, but we should be fine. Hence, my UK, which is, what is my UK? Fk plus 1 Fk, Fk plus 1 Fk is this PdK P inverse multiply with 0 1, sorry 1 0. So this is equal to 1 over square root 5 the above term will be lambda 1 power of k plus 1 minus lambda 2 k plus 1. The below term will be lambda 1 power of k minus lambda 2 power k. And we are done, because we have this fk plus 1 is equal to 1 over square root 5 of this, or you can also say fk is just 1 over square root 5 of this. Okay, so yes, we have proved this. Wow, 30 minutes. It's very long, but yeah, it is difficult, but hope it is clear. Yeah, this is difficult. Okay, but yay.